A linear transformation of vectors has the following two properties. T of u plus v equals t of u plus t of v. T of a times u equals a times t of u. And those properties must be true for all vectors u and v in the domain of T and for all real numbers a. And in this video I'm going to demonstrate graphically that for linear transformations which map from R2 to R2, the following facts are true. They map the origin to the origin, which means they don't do translations. They map straight lines to straight lines, which means they don't create curves. They map equidistant parallel lines to equidistant parallel lines, which means they treat the whole plane uniformly. The only properties of a linear transformation that we are allowed to use are those in the blue box, because they are the only properties which are true for all linear transformations. A linear transformation which maps from R2 to R2 can be described formally like so, where R2 is the set of all ordered pairs, and that set describes all vectors in the xy plane. First, we're going to review how we describe straight lines using vector equations. So here in the diagram, we have a picture of R2 with a line. Any point on the line corresponds to a position vector, r of lambda. So r of lambda is the position vector of an arbitrary point on the line. We vary lambda to locate different points on the line, and lambda can be any real number. So for example, the position vectors r of 0, r of 1, r of 2, r of 2.5 are as shown on the diagram. To define r of lambda, we choose a fixed point P on the line with position vector P, and we choose a direction vector D that points along the line. Then we stretch D by a factor of lambda to create lambda D, and finally we construct r of lambda as r of lambda equals P plus lambda D. And now we can reach any point on the line using this particular addition of vectors. P takes us from the origin to the line, and then lambda D moves us along the line to the desired point. Now we can note that r of 0 equals P plus 0D, which equals P plus 0, which equals P, so that this vector is the same as this vector. And we can note that r of 1 equals P plus D, so that this vector is the same as this vector. And finally, we see that r of 2 equals P plus 2D, so that this vector is the same as this vector. For example, we can represent the line y equals 3 over 2x plus 1 in vector form as follows. We choose P equals 0, 1, and we choose D equals 2, 3. And with these choices, r of lambda equals 0, 1 plus lambda times 2, 3, with lambda being a real number. And we can simplify this to r of lambda equals 0, 1 plus lambda times 2, 3, which becomes 0, 1 plus 2 lambda, 3 lambda. And we add those vectors to get 2 lambda, 1 plus 3 lambda. Now we can write r of lambda in xy component form as follows. R of lambda equals x of lambda, y of lambda, with x of lambda being the x component and y of lambda being the y component. And so we have that x of lambda, y of lambda equals 2 lambda, 1 plus 3 lambda. And by choosing different values of lambda, we can extract the xy coordinates of any point on the line. So with lambda equals 0, we get the point on the line 0, 1. with lambda equal to 1, we get the point on the line 2, 4. And with lambda equal to -1, we get the point on the line -2, 2. So first, we demonstrate that linear transformations map the origin in the domain to the origin in the range. Graphically, we want to show the following. The origin in the domain is mapped by a linear transformation t to the origin in the range, so that 0 in the range equals t of 0. And we use the fact that if t is a linear transformation, then t of u plus v equals t of u plus t of v, and that must be true for all u and v in the domain of t. So we let u equal v equal 0, so that t of 0 plus 0 equals t of 0 plus t of 0, and we note that 0 plus 0 equals 0. So that statement above reduces to t of 0 equals t of 0 plus t of 0, and now we subtract t of 0 from both sides, so that t of 0 equals t of 0 minus t of 0, and we note that a minus a equals 0 for any vector a, and so finally we have that t of 0 equals 0 as required. We now show that linear transformations map straight lines in the domain to straight lines in the range. And we know that we describe a line using the vector equation r of lambda equals p plus lambda d, with lambda being a real number. And so we need to show that when we map the line, which is described as r of lambda, from the domain to the range, then we produce a new line. And in fact, this is quite easy. So we map r of lambda using the linear transformation t, but since r of lambda equals p plus lambda d, then t of r of lambda equals t of p plus lambda d. Now we apply the fact that t of u plus v equals t of u plus t of v for all vectors u and v, so that t of r of lambda equals t of p plus t of lambda d. We now apply the fact that t of au equals a times t of u for all vectors u and all real numbers a, to get t of p plus lambda t of d, where we have pulled the real number lambda out of the second term, t of lambda d. Now, t of r of lambda is simply some vector in the range, and we call that r range of lambda. It is the vector equation of the line mapped to the range. T of p is some fixed vector in the range, and we call that p range. And t of d is the direction vector mapped to the range, and so we call that d range. And having chosen those names, then the equation above becomes r range of lambda equals p range plus lambda d range. And this has the form of a straight line, i.e. it has the form of the equation shown at the top of the page. And so we are done. And now we can illustrate graphically how a linear transformation maps straight lines to straight lines. So on the left in the domain we have a straight line which is defined by the vectors p and d, where d is the direction vector, and the linear transformation t maps p to p range and d to d range. In the domain the line is described by r of lambda which equals p plus lambda d. r of 0 equals p, r of 1 equals p plus d, r of 2 equals p plus 2d. And those are mapped to the range as r range of lambda equals p range plus lambda d range, r range of 0 which equals p range, r range of 1 equals p range plus d range, r range of 2 which equals p range plus 2d range. And on the diagram on the right we see that those vectors define a new line in the range, which is our range of lambda. Finally, we show that linear transformations map equidistant parallel lines in the domain to equidistant parallel lines in the range. So here we have a picture of the domain and range. In the domain, we have 4 parallel lines, and we are interested in 3 of them, which we will call L1, L2, L3. Since these lines are parallel, they all have the same direction vector d, and since the lines are equally spaced, then they are identified by the vectors p, 2p, and 3p. And so these 3 lines have equations r1 equals p plus lambda d, r2 equals 2p plus lambda d, r3 equals 3p plus lambda d. We already know that a straight line in the domain is mapped to a straight line in the range. Also, in the range, each line will clearly have direction vector t of d, so the lines in the range will be parallel. Finally, p maps to t of p, 2p maps to t of 2p, which equals 2 times t of p, since we can pull constants out of the linear transformation. 3p maps to t of 3p, which equals 3 times t of p for the same reason. And from that, we can see that the line spacing in the range is t of p, so the lines are equidistant in the range. So graphically, the mapping looks as follows. We produce 3 parallel lines, L-1, L-2, L-3, and these lines are parallel since they all have direction vector t of d, and they are equally spaced because they are located by the vectors t of p, 2t of p, 3t of p. And so we have seen that linear transformations map equidistant parallel lines in the domain to equidistant parallel lines in the range.